EMSOFT 8, which is on theory and control. So we have 4 very interesting papers here, and we will get started with the first one. So the first one will be presented by Nicole Fronda from Oregon State University. So she is a PhD student there, and her research interests are inferring temporal logic specification from data, and she is using such techniques to design cyber-physical autonomous system with a focus on safety and robustness. So without much delay, so over to you, Nicole.
Okay. Let me know if you can see my screen and hear me okay?
Yes.
All right, perfect. Thank you. As you said, I'm Nicole Fronda, and I will be sharing about our work called Differentiable Inference of Signal Temporal Logic. So suppose we have a legacy system, this autonomous UAV, that we want to use as a reference in creating a new improved version of this UAV, version 2, that we can call it. And perhaps this one is more capable, it flies faster, is more stable. And the original system has some good desirable behavior that we want to replicate in our new system, V2. So if we can identify and characterize that good behavior with a formal logical specification, then we can use that specification in design and testing of our new system. However, we may not always have access to the original specifications for the system, so we won't know how to express this good behavior in formal logic. Therefore, we will need to infer that specification for desired behavior using logical inference of the data or signal traces generated by the system. Existing logical inference methods typically conduct search over the structure of the formula first, and then search over the formula parameters. So a formula structure or template refers to the form and order of the atoms and operators in the formula, and the parameters refer to the values that need to be filled into the template in order for the formula to have a full meaning. So here's one example of a logical inference method from literature that accomplishes it through enumeration. First, they enumerate all possible templates of a formula up to a certain formula length into a database. And then one by one, a template is picked from the database, initial parameters are set, and then evaluated for how well the formula distinguishes between the good and bad behavior of the system. And this is measured in terms of misclassification rate, or MCR. If a low enough MCR is found, then the formula is returned. Otherwise, assuming monotone formulas, a search is done over the parameters to try to improve MCR. However, if MCR cannot get any better just by tuning the parameters of the template, then a new template is chosen and then the process repeats. So this method does a complete search over the formula space because it enumerated all formulas up to a certain length, but this can face combinatorial runtime explosion if the feature space is large and the number of templates to check in the database increases exponentially. Another method that accomplishes logical inference organizes fragments of the logic into a graph or lattice shown here, where edges of the graph connect less permissive templates to more permissive ones. And then this lattice is grown and pruned, and templates are evaluated by their parameters are evaluated for each template until one with low enough MCR is found. So as with the enumerative method, the formula search is done in 2 parts, first over the formula structure and then over the parameters. In this case, only templates that fit within the lattice structure or within the fragment of the logic are evaluated and searched over. So we propose a neural network architecture for conducting logical inference. And this would be able to conduct template search and parameter search simultaneously using gradient descent. We specifically use a recurrent neural network because we were interested in temporal behavior, and RNNs are excellent at processing sequential data like signals over time. We call our network a formula extractable recurrent neural network, or FERN for short. And the building blocks for FERN are based on robust semantics of past-time signal temporal logic, or PTSTL. We can train the Fern network as a classifier that distinguishes between the good and bad signals of the system. But of course, any network architecture can be trained as a classifier. However, in building the PTSTL semantics into this network, then after training, the learned weights can be extracted in a way that produces a readable formula that describes the desired system behavior. So now we show how Fern can learn the formula parameters. As I said, Fern learns formulas in PTSTL. So given a structure or template of a formula built from this PTSTL syntax, we use the robust semantics of the syntax to learn the formula parameters. Robustness is a measure of how close or how far a signal is to satisfying some specification phi, with positive values of robustness indicating satisfaction of the specification and negative robustness indicating violation. With this notion, we can train the RNN instead of using binary labels with robustness labels instead, and effectively accomplish the same thing as if we used the binary labels, as the sign of the robustness value indicates the RNN's classification of a good or bad signal trace. And in this case, a good trace being one that satisfies the specification phi, and a bad trace being one that violates it. So in this way, the RNN becomes a representation of the formula. We show here an example of how to compute robustness for a single atomic proposition mu within a Fern cell. So this cell takes in a signal input X and outputs a robustness signal R. And this signal can then be passed to other Fern cells that together with the atom will make up a whole formula. And then that string of Fern cells would output a robustness value that represents the robustness of the formula with respect to the signal input. So for this particular Fern cell, it computes the robustness of mu by multiplying the signal input X with weight vector W and then adding bias B. So during training, as we learn the values of W and B, we effectively learn the value of mu in the formula. And all other PTSTL operators have a similarly associated Fern cell with it that computes robustness. Now we show how we can learn not just the formula parameters, but the full structure of a PTSTL formula. And we do this using choice blocks, which are a special type of Fern cell that enable the network to choose which atoms or which operators belong in the formula. So in this example, we have two atoms, mu1 and mu2, and their respective Fern cell. And these are producing robustness values that are going in as inputs to this choice block on the right here. And this choice block has the task of deciding which of these atoms belong in the formula phi. Both robustness inputs to the choice block get assigned a weight W1 and W2. And these weights are, of course, real valued weights. So in order to force a choice between these inputs, we apply a one-hot quantization to this weight. So exactly one of them becomes either 1 or -1, and the other one becomes 0. And the input with the non-zero quantized weight is the one that's chosen for the formula. So now we see the whole picture and how we can use gradient descent to learn both the structure of the formula and the parameters at the same time. The structure being which atom belongs in the formula, and the parameters being the actual value of the atom. And choice blocks can be used to select not just between atoms, but also between operators or between sub-formulas, and then also between multiple formula templates. So in this way, Fern isn't restricted to learning any particular template. We now compare Fern's performance with the enumerative and lattice methods we saw previously in binary classification tasks across different data sets. And we evaluate the MCR and runtime of all three methods, as well as take a qualitative look at the formulas learned. So here we show two examples from real data sets. The two graphs on the top here depict the MCR comparison of the different methods for different formula lengths, and the bottom graphs here depict a runtime comparison. for this HAPT data set, we see that Fern yield a lower MCR, which is better than the lattice method, and as good MCR as the enumerative method on most lengths. However, it did have a much higher runtime than the other two methods. For the larger lift data set, we see that Fern yielded as good or better MCR than the lattice method, and it was able to do this actually at a quicker runtime than the lattice method. And while the enumerative method wasn't able to produce results before timing out. And here are the best formulas in terms of MCR found by each of the methods for the HAPT data set, a sample of the traces for which are shown on the graph here. The green traces indicate dynamic movement in the X direction as gathered by HAPT smartphone data sensors, and then the red traces indicate static movement. And so the task here was to try to classify between the two sets of traces. And we see that the Fern and enumerative methods were able to perfectly classify the data. They actually found almost like quite similar formulas, while the lattice method, because it's restricted to this, this form of formulas, only the right-hand side of the formula, which is the classification subformula, is able to distinguish between the two sets of traces. So some key discussion points for our work are that even though the Fern network is architected to compute robustness, it can be trained on binary labels to learn formulas. We also note that domain knowledge can be used to inform design of the Fern architecture. For example, knowing which features are relevant ahead of time can inform how to architect certain inputs into choice blocks. And it's with these choice blocks that Fern is able to conduct the template search and parameter search in logical and formula inference simultaneously. We found that training Fern is time intensive, but that it also can scale better for larger data sets like the lift data set. We also found that in our experiments, different formulas can yield the same or very similar MCR, which indicates that further research is required to explore more appropriate metrics beyond MCR for evaluating logical inference. Also, that several formulas were really simple, suggests a need for richer selection of data sets in logic inference research as well. So to summarize, this work presents a new differentiable method for learning STL formulas that we called Fern. And we evaluated this method through a systematic comparison against existing formula inference methods to find that it performs as good or better than these methods. And future work includes embedding a formula equivalence check in the Fern architecture, as well as discovering a more efficient quantization procedure for the weights. So that concludes my talk. Thank you for your time.
Thanks for the presentation. We have time for a quick question.
Yes, I have a question for the speaker. Thank you for the presentation, and it's a very interesting work. I have a couple of questions. Okay, first of all, for the choice box. Okay, in order to select, the parameters and other things through the choice box, are you going to have an expanding number of choice boxes in your network? And how does it affect your time complexity here to get the results, get the output? I mean, the robustness, right?
Right. So I'm not sure I can. So we did take a look at runtime, but I don't have a grasp on the added time complexity for each new choice block. But you can chain choice blocks together, as I think you were was the question, and that yeah. Oh, sorry.
Actually, for your experiments, how many choice boxes did you have in your RNN and for your experiments?
Right. So we learned up to formulas of length 6. So that would be at least 6 layers of choice blocks, essentially.
6 layers of choice boxes. And do you have a comparison on the time performance? for the traditional method and this neural network method?
Right. So I have runtime here is training time for the neural network, and then for runtime for the existing enumerative and lattice traditional formula inference methods, that was the time to run the algorithm. So you can see that it does typically take much longer. So this x-axis, or sorry, y-axis is seconds. For larger data sets, though, processing took a lot. We found that it actually could be shorter for network than for some of the other methods. But typically it was much longer to run or to train and find. Yep.
Yeah. So, but considering the training time, how large is the training set you have here?
So the largest was this lift data set, which was probably like a few tens of thousands traces, and the smallest probably was this HAP data set, which was around 500 or so traces.
Okay, so then you have to, almost emulate all the possible routes, right? For the input of this RNN. Going through the enumerate all the routes and use it as a input for the RNN, right?
Are you asking about the lift data set, or sorry, maybe I'm not understanding the question. Sorry.
Okay, sorry, but yeah, I'm actually interested in what kind of input you have for this neural network.
Oh, they are. So for the HAPT network, there was just one-dimensional traces, or sorry, for the HAPT data set, and for the lift data set, it was two-dimensional traces, so XY position of the cars.
Okay. So you basically, to produce those traces, you have to go through all the possible paths, right? And in your graph, for this formal verification purpose.
I think the data set perhaps is already available, if I understand correctly.
Yes,
and this data set is used for training the network, and then then the network is used for inference. So it's not like he has to generate the data for producing the data set.
Correct. Yeah. Sorry. Exactly.
Thank you. Thank you.
Sure.
Okay, so let's take all the other questions and during the poster session. So can the next speaker, Liren Young, share the screen? So the second presentation would be by Liren Young. He's a lecturer in Huazhong University. After finishing his PhD and postdoc at University of Michigan, he joined as a lecturer. His research interests are in control theory and formal methods, with its application in verification, control synthesis and falsification in Inceptive critical cyber physical system. So over to you.
Hey, thank you for the introduction.
We can hear you.
Talk about efficient. Can everyone see my slides, by the way?
Yes.
Okay, so the title is Efficient Backward Reachability Using Minkowski Difference of Constraint Zonotopes. This is a joint work with my collaborators at the University of Wisconsin-Madison and University of Michigan. So this paper is motivated by developing design analysis tools for safety critical systems with continuous state space. The systems can be viewed as the closed loop on the right. And we're interested in two types of problems. One is the falsification problem, where we're given this closed loop system together with a specification, and we're looking for an initial condition together with a sequence of external disturbance inputs, under which the trajectory violate this given spec. And if we can do so, then we quickly identify bugs in the controller and we falsify the system. The second problem is synthesis, where we're just given the open loop system. And we want to find a controller so that if I close the loop with this controller, I'm guaranteed to satisfy the requirement starting from a set of initial conditions, regardless of the disturbance. So one observation we make here is actually many falsification and synthesis algorithms use the so-called backward reachability analysis or backward reachable set computation. So what is a backward reachable set? This is a set of initial conditions or a set of a subset of your state space from where you have a control strategy to steer your trajectories into a given target set, regardless of the disturbance. And like we said before, this is really the basic building block for many synthesis and falsification algorithms. In fact, in this EMSOFT paper last year, we have shown that you can use this type of computation to falsify a vision-based neural network controller. For example, this is the normal behavior of the controller, so it is able to avoid the obstacle in the front. And if you use this backward reachability analysis, we're able to find this weird safety violation in the middle. So how do I compute it? In theory, you can compute it using this pre-operator recursively. So this operator gives you the set of states from where you have a control input, so that for all disturbance, you're guaranteed to go to the target in one step. Then you can do this recursively, and in the end, the overall backward reachable set is just the union of all of them. But in practice, if you want to do this computation, it might be challenging due to the curse of dimensionality and nonlinearity. So on the other hand, we have seen that for forward reachability, there are actually some fairly efficient tools, even for high dimensional and nonlinear systems. So the key question we want to ask here is, can we use those for backward reachability? And to answer this question, we have a brief comparison here. So there are two differences between the two. One difference is the following. Here in the backward analysis, you have two inputs to the system. One is the control input, the other is the disturbance input. And therefore, they are playing against each other. This is a two-player game. On the other hand, for the forward reachability, you only have one input, the disturbance. So this is really just a one-player game. That's the first difference. The second difference is the following. So in backward analysis, usually it makes more sense to do an under approximation or inner approximation whenever the exact computation is impossible. This is because if you can get this inner approximation, then the control law derived from this inner approximation will work for the real system. On the other hand, for the forward analysis, this is not the case. So usually we need to do an outer approximation so that if I verify the system to be safe using this outer approximation, the same result will hold for the real system. So those are the two differences. The implication here is the following of these two differences. For backward analysis, this two-player game nature leads to an extra Minkowski difference step in the computation, and we will see what that means in a minute. So this Minkowski difference step is missing in the forward analysis, but the forward analysis is easy because we have some very efficient set representations, such as constraint zonotopes, so that we can do computation quickly. And therefore, if you want to use those for backward analysis, one thing you need to do is to do this Minkowski difference computation for constraint zonotopes. And now the question is, can we do that efficiently and can we do that exactly? And if the answer is no, then can we at least under approximate it efficiently? Because like we said before, for backward analysis, what makes sense is to do under approximation. So with that, finally, can we use this under approximation technique to do backward reachable set under approximation? And here are our answers. It turned out that no algorithm can achieve efficiency and exactness at the same time. And therefore, we propose an efficient way to under approximate the difference. And then using that, we develop some scalable algorithms to under approximate the backward reachable set. And it works even for high dimensional nonlinear systems. So that's the big picture. In what follows, I will jump into a bit more details. And this is our problem formulation. We have this discrete time nonlinear systems, and we're going to assume the target set and the control input set. to be so-called constrained zonotopes, and we will define that in a minute. Further, we assume the disturbance set W is a zonotope because usually it is symmetric. And finally, the safe set is assumed to be a polyhedron. Or in an extended version of this, we assume it is a union of finite many polyhedron. So what is a constrained zonotope? This is a polytopic subset of your state space. And you can think of it as the image of an affine map of the intersection between the unit box and the affine space. So here the GC matrix is defining this affine map, and the AB matrix is defining this affine space can be used to fully characterize the set. So this tuple here, GCAB, is called the generator, the constraint generator representation of the set, and CGREP for short. Moreover, one thing here is if the AB matrices are not here, then the set is just called a zonotope. So given the setting, how do I compute the backward reachable set? If your system is linear, then you can see that all you need to do is to compute this pre, and that amounts to the following computation. And for nonlinear dynamics, you can still linearize the system. And what you need to do is to replace this disturbance set W by a larger set that combines the impact of the linearization arrow and the disturbance. So here, there are several set operations involved. For example, affine map, intersection, Minkowski addition, and Minkowski difference. The good news here is for the first three, you can do this fairly efficiently if you work with constrained zonotopes. This can be done by the so-called CGREP manipulation. So the complexity is just linear in the input data size. Whereas it is not clear if the same can be done for the Minkowski difference. And this is the key question we want to ask here. So here are our answers. It turns out that given the CGREPs of your minuan and the sub-VN, there is no algorithm can find a polynomial size CGREP of their Minkowski difference in polynomial time. Of course, unless P is equal to NP. So this is a bad news, so we cannot do it efficiently and exactly. And this is why we have theorem 2, where we propose to find the end approximation using a linear program. So here, the number of variables and constraints in this linear program is polynomial in the input data size. So this means you can solve it efficiently, and the resulting end approximation is just also has a polynomial size. Finally, we also analyze how conservative this end approximation is. So we can show that for every minuan, you can find a rich enough CGREP for it, so that if you use this CGREP in your computation, then our end approximation is actually exact. But of course, this rich enough CGREP might be very large sometimes. So there is apparently this trade-off between accuracy and efficiency. And this trade-off can be tuned via CGREP selection. So those are our answers to this Minkowski difference and approximation. And using that, we developed some algorithms to under-approximate the backward reachable set. So here we have two sets of algorithms. One is called the scaling method, the other is called the splitting method. The key challenge here is you need to over-approximate the linearization arrow which must be valid within the set you compute before computing these sets. So this is the main challenge. In the scaling method, what we do is we scale or we enlarge this arrow set by a scaling factor every time until it is large enough so that it will be valid within the set. Or in the splitting method, what we do is we will keep the size of the arrow set and we will partition the target set until every small piece is small enough so that the given arrow set is valid within it. So here the scaling method is better for longer horizon computation. And the drawback is sometimes it might be conservative, meaning it gives smaller sets, where it is the opposite for the splitting method, and it also handles non-convex environments. So those are our algorithms. I have some experimental results here. So the key message here is our method is less conservative than zonotope-based approach. It also deals with constraints, including convex and non-convex ones. And also finally, comparing to some off-the-shelf tool like the HJB toolbox, we are much more scalable, and we're able to handle relatively high degree systems. So let me wrap up. In this paper, we use constraint zonotopes to develop some scalable algorithms to do backward reachable set and approximation. And those end approximation can be used to do control synthesis or falsification with some temporal logic requirements. Our results is less conservative than zonotope-based approach, and we're more scalable than HJD method. The key technical ingredient here is a efficient way to under-approximate the Minkowski difference of constraint zonotopes. And we also find that there is a trade-off between accuracy and efficiency in our algorithm, and we plan to explore that in the future. And with that, I would like to thank you all and take any questions.
Thank you for the nice presentation. So we have time for one quick question from the audience.
Hello, here I have a question. So I personally like this work, and here my question is that in this work we developed a new algorithms, right? So what's the time complexity of this algorithm, and is this already implemented and deployed on real-world devices to evaluate the performance of overhead model?
Are you talking about the algorithm for Minkowski difference?
Or yeah.
The Minkowski, okay.
Yeah.
So in that algorithm, we solve a linear program, and the number of constraints and variables are polynomial in the input data size, meaning the CG refs for the subject and the minuend. Therefore, it's polynomial, but I don't have a detailed complexity analysis, but it's polynomial. And we also implemented in MATLAB. So we will make it public, but right now it is not public. Yeah, and we're working on using it for falsification and synthesis.
So in the future, maybe our team will open source the work.
Yeah, it is in MATLAB, and we will make it public.
Okay, thanks. That's great.
Thank you. Thank you for answering.
Okay, thank you. Let's take the other question during poster session. The third speaker, Shuangshuang, could you share your screen? So she's the next speaker is Shuangshuang. She is a PhD student at Northeastern University, and her research interest is in embedded real-time system and real-time scheduling theory. So she will be presenting her paper shortly. What to you?
Can you hear me now?
Yes.
All right, let's get started.
Yeah.
Hello, everyone. I'm Chang from Northeastern University. I will give the presentation of our paper towards minimum WCRT bound of DAG tasks and prioritize the least scheduling algorithms. To meet the rapidly increasing computing demands and lower power consumption, multicores have become the mainstream hardware for embedded real-time systems. To fully utilize the capability of multicores, software must be parallelized. Good parallel programming frameworks can great help. For example, OpenMP, TBB, and so on. DAG is a popular model for real-time parallel applications. Almost all modern parallelism frameworks support DAG tasks that can capture fine-grained and irregular parallelism. For the research on DAG, the challenge problem is how to reduce the worst-case response time, whose abbreviation is WCRT of DAG tasks. Graham bounds the WCRT by using the longest path and the volume of the DAG. Look at this picture. This is the longest path as a critical path. All vertices of the DAG, except those in the critical path, may block the critical path. And recently, we observed that assigning priorities to vertices will significantly reduce the WCRT of DAG tasks. Look at this picture. We assign the different vertices by different priorities, which have high priority and low priority. Only the vertices with high priorities can block the critical path. As a result, the WCRT of DAG tasks will be reduced. Researchers propose different priority assignments and they derive different WCRT bounds. Therefore, an open problem is what priority assignment, whose abbreviation is PA, can derive the minimum WCRT bound. So this is our target. This paper shows the minimum WCRT bound defined as follows. This part is the WCRT derived by the specific priority assignment when pi is the critical path. And this part denotes the maximum WCRT among all paths under the specific priority assignment. The whole formula is to find the minimum WCRT among all priority assignments. The R star is what we want to solve. In this paper, we develop an integer linear program to solve the R star. The key points are as follows. First, we use the path of the DAG as a constant and use vertex priority as a variable. And what we want to do is to express the WCRT of a given path pi related to a specific priority assignment. For the constraint, there are many concurrent path constraints we use to formulate the WCRT under the specific priority assignment. Here, we want to calculate the maximum WCRT bound among all paths. The objective function is to minimize the WCRT among all priority assignments. That is to solve the R star. First, we want to show for each path how to express its WCRT bound. We formulate it the sum of vertices width. Here, it is the weight of vertex Vi. The weight of vertex is defined as follows. First, the weight of Vi equals its worst case execution time if Vi is in the critical path pi. Second, the weight of Vi equals 0 if Vi is not in pi and its priority is lower than all parallel vertices of pi. Third, this is the weight of Vi if Vi is not in pi and its priority is higher than some parallel vertices of pi. By using priority variables and auxiliary variables, we can calculate the weight of Vi like this. For each path pi, we derive the constraint below. This constraint ensures that the value R is no less than the WCRT bound of path pi under the specific priority assignment. Look at the picture. Each path is associated with a path constraint. By combining all path constraints, R is able to calculate the maximum WCRT that is related to a specific priority assignment. Finally, the objective function can minimize R, and that solves R star like this. The summary of the IRP model. This is our objective function, and the basic constraints define the priority relations between vertices. Path constraints are used to compute the weights of vertices based on the priority relations of vertices and bounds the WCRT of each path under the specific priority assignment. However, the number of basic constraints is polynomial and the number of path constraints may be exponential with the size of the DAG. The challenge problem is how to deal with the exponential number of path constraints in the IRP model. Our technique is to solve the IRP model iteratively. Initially, only consider one path constraint and then add a new path constraint at each iteration until getting the minimum WCRT bound. In more detail, our iterative solving method contains 4 steps. The first step, we solve the IRP model with basic constraints and one path constraint. Look at this. we use one pass constraint to solve the current IRP model and achieve the current solution, which is the lower bound of the R star. We should know that the current solution is not the final solution of our IRP model because there is only a single path in the current model in step 1. In order to solve the optimal R star, we should involve more paths. In later steps, we should involve the paths one by one that continues to refine the solution. The second step, detect the path that worsens the WCRT bound under the current priority assignment. The current priority assignment is P3 here. In the third step, we add path constraints that are related to our detected path P3 and resolve the IRP model like this. So we consider 2 paths in our model. By repeating step 2 and step 3, we can solve our IRP model iteratively until no path worsens the WCRT bound. Next, we will introduce our evaluation results. We conduct the experiment with different configuration of the parameters. Here, N is vertex number, M is the curve number, delta is vertex in or out degree. The evaluation result shows our method can solve the minimum WCRT bound optimally within a few minutes on average. When obtaining the minimum WCRT bound, only 13% of paths are involved. Our method can obtain nearly optimal WCRT bounds even if involving only very few paths. The gap between optimal and nearly optimal WCRT bounds is less than 3% when the curve number is larger than 8. Finally, the conclusion. Assigning different priorities to vertices is a promising way to reduce the WCRT bound of DEX. In this paper, we propose an IRP model which can derive the optimal priority assignment. After that, we develop an iterative solving method to efficiently solve the IRP model and achieve the minimum WCRT bound. That's all. Thank you for your attention. I would be glad to answer any questions.
Thank you for the presentation. So we have certainly time for questions.
Hello? Hello, can you hear me?
Yep.
Hello, thank you for your presentation. And I have 2 questions. The first one is, if I understand correctly, your proposed integer linear programming model and iterative method are only suitable for a single DAG task, right? And the second one is the objective function is to minimize the WCRT bound. And why does it detect the path that wasn't the WCRT path in the bound in the second step of the iterative method? Thank you.
Okay, thank you for your questions. For the first question, in our paper, the IRP model and iterative method are suitable a single DAG task, but actually our method can be easily extended to response time analysis of periodic DAG tasks with implicit deadlines. For example, under federated scheduling, each DAG task is executed on several pre-assigned processors. On the one hand, the job released by a DAG task is not blocked by the job released by other DAG tasks, since any two DAG tasks are isolated by their dedicated processors. On the other hand, This is no interference between two jobs released by the same DAG task due to implicit deadlines. Then we can obtain the WCRT bound of DAG tasks. For your second question, can you repeat it again?
Okay. Just I'm wondering why it detected the path that wasn't the WCRT bound in the second step of the iterative method. As I understand, your objective function is to minimize the WCRT bound, but it seems it conflict each other. That's my question.
Okay. Because in the iterative solving method, the first step, the IRP model, which only contains one path, just can derive the lower bound of the minimum WCRT bound. So then, at each iteration, we increment the IRP model with the path constraints, which are more likely to derive the optimal priority assignment. And the objective value R of the IRP model continues approach to the minimum WCRT bound. So this is my answer. Do you have any questions?
Thank you very much.
Okay.
Thank you. So let's save the other question for the poster session. So maybe the next speaker, Gaoyang Dai, can share the screen. So the next speaker, yeah, hello. The next speaker is here. Yes. Okay.
Hello, can you hear me?
Yes. So Gaoyang is a PhD student at Uppsala University in Sweden. After finishing his bachelor and master's from Northeastern University, and his research interests are in modeling and schedulability analysis for real-time embedded system. Over to you. Thank you.
Thank you.
We can hear you.
Yeah, can you see my slides?
Yes.
Yeah, thank you. Hello, everyone. My name is Gaoyang Dai. I'm a PhD student from Uppsala University. It's my pleasure to be here and briefly present our work. For many parallel applications, it's naturally can be modeled as DAGs. So in this work, we focus on the sporadic DAG task model with non-preemptive nodes. As shown in this example, each node of a DAG is associated with a worst-case execution time. So the tasks have a relative deadline D1 and a minimum inter-release time T1 here. It releases infinite sequence of instances called jobs. So if we assign this DAG in one core, then we can have some a schedule like this. It's clear that this is not schedulable. N4 missed the deadline. But if we try to schedule this on two cores, the schedule looks like this. Right, we can run N2 and N3 in parallel, and then it's schedulable. And the task can release another instance after 6 time units. And here in this example, it releases another one at time 9. And it's also finished before the deadline. So in if another task exists in the system and has a lower priority here at P2, then the first task. Recall that all nodes are non-preemptive, and also now for each DAG has a fixed priority assigned. Then if we schedule them again on 2 cores, the schedule could looks like this. Then it's clear that this green DAG also missed the deadline. And actually, the worst case response time of this green DAG is 7. So for a large system, to get an exact WCRT or worst case response time, it's intractable in this setting. So if we analyze the elements of the WCRT in this simple example, we can get this equation. This R1 equals to, maybe one pass from the source to the end node, the execution time of one pass, plus some interference. So here, this is the execution time of N2. So if we can't get an exact response time, can we have some upper bound? Yes. The existing method proposed the following idea to bound the WCRT. Use the longest path and compute the possible interference from lower or higher priority tasks. So here in this example, we only have self and the lower priority interference, but assuming if we have a higher priority task, and then we could possibly have a higher priority interference, which means this higher priority, this blue block can preempt the green one, which can have more interference. So in this idea, the response time bound becomes this. It includes the self-interference, lower priority interference, and the higher priority interference. For the self-interference, it equals to the total WCET of the DAG minus the WCET of the longest path. And for the higher priority interference, assuming that tau I is a higher priority task than tau k, within the schedule window T of tau k, the maximum higher priority interference is observed when the first job executes as late as possible until its WCRT, and starting execution aligned with the release time of tau k, and for the other jobs of tau I, execute as soon as possible. Note that in order to derive the bound, WCRT of tau k and tau I are also needed. So for lower priority interference, the key question is how many times the green can be blocked by the pink. So based on the old method, if we check this example, a blocking can happen when there is a branching in the green DAG, namely when it asks for additional cores. But the core is occupied by a lower priority job. Here it's N6. Or if there are higher priority tasks preempting the green task, blocking can also happen. Consider all of the possible blocking scenarios, a lower priority interference bound can be derived. This is, however, a fairly pessimistic bound. So as a result, the method computes the WCRT by this formula. A fixed point calculation is needed because you see on the right-hand side, you also have the response time R to calculate the response time on the left-hand side. So next, I will explain our new idea of computing this bound. Let's go back and have a look at the example. So from this worst case schedule, if we go from the end node and consecutively add the latest finished predecessor nodes, we can obtain a critical chain. So here we go from N4 and N3, then N1. Then we get a critical chain lambda for this green DAG. The critical chain has a good property. The blocking can only happen between the nodes in the critical chain. So in this example, only these 3 red arrows can have the blocking. Based on this, we propose a new bound on the WCRT, which is this one. We use this critical chain in this formula. But however, the critical chain is unknown as we don't know the worst case schedule. But we can use a path that dominates the critical chain to derive a safe WCRT bound. Because we want to bound the worst case response time, so the equation is the equation to compute this path can be derived as this. The blue block is eliminated as the higher priority interference does not depend on the critical chain. We propose a dynamic programming algorithm that traverses the DAG to compute the lambda max. So you can check details of this algorithm in the paper. So after computing this lambda max, we can rewrite the WCRT bound as this new formula. So this is for the fixed priority scheduling policy. So a fixed point calculation is also needed. So for EDF scheduling policy, we propose a new response time bound, which also follow the same structure, but the computation of the lower priority and the higher priority interference has to be changed. So for the higher priority interference, consider that first, all of the other tasks could interfere with the tested task as higher priority interference. And then so we have to check all of the possible tasks under other than the tested task tau k. So record the higher priority interference computation for the fixed priority scheduling policy. We draw the same schedule and check that the relation is what the relation is between the absolute deadline of the job of tau k and the last job from another task tau I falling in the scheduling window t of tau k. If this absolute deadline of tau k is later, as shown here, so which means it has a lower priority, then all instance from tau I is considered higher priority interference, and this is the worst case scenario. But if the absolute deadline of tau I is later, like here, we know that the last instance from tau I is not a higher priority interference. Then we can try to shift the schedule of tau I to the left until the absolute deadline of tau I and tau k aligned like this. Then we know that the last instance of tau I become a higher priority interference. And if the first instance of tau I is not fully removed, this is the real worst case scenario. You see here we add the last instance, but we remove part of the first. So for the lower priority interference, only the last instance of tau I falling in the scheduling window of tau k can be a lower priority interference. So in this case, yes, because this t, the scheduling window includes the last instance. But if this scheduling window or this response time of tau k is very short, then in this case, the instance of tau I cannot be a lower priority job, meanwhile falling in the scheduling window. So no lower priority interference exists from tau I to tau k. And after distinguish all the possible tasks contributing to the lower priority interference, fill in the blocking points of the critical chain by those lower priority jobs can derive a safe upper bound on the lower priority interference. Finally, put the new higher and lower priority interference into the formula can compute a safe WCRT bound for EDF scheduling policy. So we have done our experiment on randomly generated task sets and on some benchmarks that shows our method outperforms the state of the art. Thank you all, and I'm happy to answer any question.
Thank you very much. So we can have one quick question. Okay, no questions from the audience. So I have one quick question. So did you, so you showed the experiment. So I was wondering whether you had done any experiment on a real application which has such properties or structure?
Real application. Yeah, we have done.
These are synthetically generated tasks, right? So are there?
Yeah, we have. Yeah, we have synthetically generated, randomly generated task sets like this, and we adjust different parameters to show the performance. And we also.
But this is not a real application. So these
this
are.
Is, yeah, this is randomly generated task sets, and also we have done these experiments on benchmarks. So here, this benchmark called Stream IT, and we basically extract 4 different DAG structures from this benchmark, and then we assign different priorities and then do the experiment.
Okay, thank you. Okay, so with no other questions, so I think this was the last presentation of this session. So thank you very much for being in the session, and we can end this session now. Thank you.
Thank you. And I just want to say also thank you to everyone, since this is the last session of EMSOFT this year. So, and of course, not everyone is here that have been enjoying some of the other sessions. So from myself and from Claire, I just want to say thank you all participants, and especially all authors of very great papers. Thank you. And the ES week is not closing, but this is the last session of EMSOFT. Do you want to say something, Claire?
No, I want to say thank you also. It was a very nice conference. Thank you all for your participation and a great presentation, and hope to see you next year with us.
Yes, and thank you all session shares as well. Okay, good. With that, we close this session, and